Alrighty. Good afternoon, lads and ladies. Welcome back to MAC 1140 Pre-Calculus Algebra. I want to say one thing before I get into stuff today, and I mentioned this quickly on the first day, but just in case anybody missed it, it looks like most folks are following it here. I want to ask strongly that you use your real name or whatever name you have on your Santa Fe ID here in Zoom, because that's how I take attendance. So I reported attendance for financial aid purposes today, and there were a few folks who I have not marked as having attended from this class, and there's also a few folks who had been signing in as like iPhone or Ainsley. Obviously, I can tell what your name is from that. Hugo, I'm pretty sure you were reported as having attended. I think you're good, but please, I'll just ask that you be consistent, sign in with your full first last name as it appears on your Santa Fe ID in Zoom. That way I can make sure the attendance records are accurate and nobody's financial aid gets held up. Because if you're not marked as attending, financial aid will withhold your money, your Pell Grants, your loans, whatever. And you don't want that to happen. I don't want that to happen. So let's make sure that doesn't happen. All right, with that said, we're going to pick up today where we left off last time. If you recall, last time we finished talking about average rates of change. The very last thing we did last time was kind of connect the notion of an average rate of change to the difference quotient. Before we do that, let's do the normal hello.
Professor.
Yes.
For the homework, I saw that it said it's due Wednesday, the second homework, but I know in class you said Monday, but I was just wondering if is it due based on what it says on the WebAssign, or is it due Monday?
So there's two homework sets up right now. The first homework set is due next Monday. The second homework set is due next Wednesday, and that's the pattern we're going to continue to follow. So you'll have homework due twice per week, once on Monday and once on Wednesday.
Awesome, thank you.
Not a problem. Okay, so we're actually getting pretty close to exam one. We're going to talk about the date for that before we leave here today. We can come back and talk just a little bit more about average rates of change today. I can spend some time taking homework questions because that's the last topic that's on the current homework set. No, that's on the next homework set. So yeah, we can start with some homework questions if you guys like. Then we're going to talk, like I said, a little more about average rates of change. We're going to talk about transformations of graphs. That's going to be our sort of main topic today. And if there's time, we're going to finish section 2.7 today on how to combine functions. That'll be fun. Once we finish section 2.8, which is the first topic for next week, we will be ready for exam one. Now, I'd like to give you a little bit of time, not too much time, a day or so between when we finish the lecture on that material and when we have the exam on that material. So for those playing the date game, I'm guessing, I'll set the tentative date right now. I'm thinking the appropriate day for exam one is going to be, we don't have class next Monday, do we? Because next Monday is taking off for the 4th. The appropriate date for exam one is most likely going to be next Thursday, the 8th. I may end up pushing that back just a tiny little bit, but let me open with this kind of announcement. All right, let's get a few things in here. Homework one is due on 7/5/21 at the time class normally begins, which is 1:15 p.m. Homework two is due on the Wednesday, so that's 7/7/21 at 1:15 p.m. And exam one will be during class time or in class on, what did I say, the 8th, right? Not Thursday? Yeah, the 8th. 7/8/21. So kind of our first round of big things coming in here next week. And again, 6-week class moves ridiculously fast. It's just how it is. So it's so important that you're spending time every single day working on the homework. That's the way to ensure you'll be prepared for the test. Work the homework problems honestly. Remember, graph functions in homework by hand unless the problem says to use a graphing calculator. I can't check that. I can't force that, right? Because WebAssign checks the homework problems, and all you have to do is pick the right graph from their collection of 4 graphs, which is a bummer. I would love to check that. I would love to say you're not going to get credit for these homework problems unless you draw the graph independently by hand. But what I can promise you is that if you don't practice graphing those functions by hand, specifically the latter set of the current homework and the transformations homework that I opened up today, if you don't practice graphing those by hand, it's going to bite you really hard on the test. So graphing is a huge part of this class. You've got to get comfy with it. And the way you get comfy with it is by drawing those graphs by hand as you work the homework problems. That's what WebAssign intends for you to do. They intend for you to graph the function and then pick the one that matches the graph that you drew. And so that's really what you need to do in order to develop the skill that's necessary to do well on the test. And I'll remind you that the tests in this class are worth a little more than 75% of the grade. So even if you rock the homework, if you don't prepare the correct way for the test, it really doesn't matter. So please graph the functions by hand. You'll thank me later. It'll take longer. I know that. But this class requires a time investment. That's just what it takes. So I promise you, if you do that, it'll pay off. Okay, today what we're going to do is talk a little bit more on average rates of change. There are some concepts in there that I want to explore with you a little bit, even though we've kind of covered all the core things. It's very much worthwhile to talk in some depth about connections between like increasing, decreasing, and average rates of change, or mins, maxes, and average rates of change. Help you build some of the knowledge that you're going to want for calculus and help you understand a little better what's going on in this class. And then we're going to move on from there. We're going to talk about transformations. I think that's the next section, right? Yeah. Average rate of change. This is section 2.4. I'm going to talk about transformations of graphs. This is not section 2.5, it's section 2.6. 2.5 is on building models out of linear functions. And really that is like a third of college algebra here at Santa Fe. I don't think anybody needs more practice with MX plus B. So I'm not going to waste your time on it. And then if there's time, we're going to talk about combinations of functions. Which I believe is section 2.7. If we don't get to combinations of functions, which is a very real possibility, then it may be the case that I bump the exam date one more day. But no promises there. Even if we don't get to this, we will have time to cover it Monday, and I think Tuesday, because Monday we're off. And then I think between Tuesday and Thursday, there's enough time for you to internalize that material. Okay, so this is what we're doing. We've got finite time, so let's do it. And getting into it, some thoughts. Average rates of change. I'll just say rates of change. First little thought. If you have a function that's always increasing, if f of x is increasing everywhere on the interval a comma b, then what can you say about the average rate of change? From x equals a to x equals b for that function. So I'm asking you to help me fill in the if-then statement. If f of x is increasing everywhere on the interval ab, then the average rate of change for that function from x equals a to x equals b must have what feature? If you're not sure, it's okay. Just throw out an idea. I just want to hear what you guys are thinking. Any thoughts?
Must be positive.
Yeah, must be positive. Why is that the case? Well, suppose I have a function, something like this. Maybe here's A, here's B. So up here's the point B comma f of B. Here's the point A comma f of A. If this function has been increasing everywhere between A and B, as is more or less drawn here, then it has to end up over here higher than it started out over here, which means that the slope of the secant line connecting those points has to be a positive slope. In other words, the net change is positive. If the net change is positive, then the average rate of change must be positive. If you swap the word increasing to decreasing, then you can swap the word positive here with negative. And the corresponding picture is what you think it is. If your function is decreasing from a to b or on the interval ab, then the slope of the secant line must be negative, because the point on the right has to be lower than the point on the left. Is the converse to this statement true? If the average rate of change is positive, can you infer that the function is increasing everywhere on the interval AB?
Can you say that again?
Sure. So the statement here is an if-then, right? If something, then something else. I'm asking, is the converse to that statement true? Can you swap the direction of the implication? So if you're increasing on AB, then your average rate of change from A to B must be positive. If I say it kind of backwards, if the average rate of change is positive, is it true that you must be increasing everywhere on AB? Or put differently, is it possible to have a positive average rate of change, but not be increasing everywhere from A to B?
No. Because like in between the interval A and B, like the line could be squiggly.
Right. Yeah, exactly. That's Benjamin's hit it on the head. The converse to 1 is not true. i.e., just because the average rate of change is positive from x equals A to x equals B, but does not guarantee the function is increasing there, increasing on AB. It means the net change has to be positive. That's true. But that's not the same thing as saying the function is increasing everywhere. And there's all sorts of examples. I'll just draw a kind of random one, generic one. I could have something like this. So here's a function where the average rate of change is certainly positive. Right? The average rate of change for this function from x equals A to x equals B is definitely positive, but we're not increasing everywhere, right? We're decreasing through a chunk of this. So, it's good stuff to think about, and I would like you to think, as much as you have the patience to do, about the connection between average rates of change and increasing and decreasing functions. There is kind of a true statement that if you shrink the interval AB down to a really small interval, then if that average rate of change, as you move the interval, the really small interval around, if that rate of change is always positive, then most likely your function is increasing everywhere. But it requires thinking about many small intervals instead of just one kind of regular sized interval. What else did I want to say about rates of change? We talked a little bit about units. Maybe a question. What kind of functions have constant rates of change? On all intervals. So imagine I tell you that I've got some function here, f of x. Its average rate of change is 5, no matter what interval you're looking at. What can you tell me about that function?
It's gonna have a slope of 5.
Good. Good. What kind of functions have slope?
Linear.
Yeah. So if f of x has average rate of change always equal to 5 on all intervals, we can deduce two things. One, f of x is linear. That's a big deal. And two, the slope of the line is 5. So what kind of functions have constant rate of change on all intervals? Linear functions. So what are we saying about nonlinear functions then? Well, they must have rates of change that vary, right? Depending on where you look, the rate of change for a nonlinear function could be all sorts of different things. Right, questions on these two little kind of comments or notes? Okay. Then I think we're ready to move to the next little thing. So let's go ahead and do that. We're going to go ahead and leave section 2.4 and move on to section 2.6, which is where we're going to be talking about transformations. So what does it mean when I say I'm going to transform a graph? What are we talking about? Well, it's a procedure for getting a graph of a new function from a graph of an old function. So you remember those kind of basic functions I graphed for you the other day? X squared, x cubed, x to the 4, x to the 5. We looked at some families of basic functions, power functions. We looked at the square root graph, the cube root graph. We looked at 1 over x squared. We said, you know, these kind of form these nice big families of graphs, and we're going to learn how to get other graphs from those. Here we go. Section 2.6. Transformations of functions. Graphs. We kind of recall, we know the graphs of y equals x squared, x cubed, x to the 4, x to the 5, and so on. We know the graphs of the square root of x, the cube root of x, the 4th root of x, the 5th root of x, and so on. We know the graphs of 1 over x, and 1 over x squared, and 1 over x cubed, and so on. There's a few others. I'd say these. Together with the absolute value function. Is there anything else that we use as a parent here? I think that's about it. And linear functions. Form what we will call a collection of parent functions. Later, I'm going to be adding some exponential and logarithmic functions to this list, but these are the sort of the graphs that we should know. Right? If you don't remember what any of these look like, you need to go back and add them to your notes. We looked at these and these and these explicitly in class, I think 2 days ago. If you want to take a look at some of the ones I've listed there that we didn't look at explicitly on that day, I'd be happy to show you. They follow the same sort of patterns. So for example, right, the even powers of x all have this kind of bowl shape. Only x squared is a parabola, but like x to the 6 here, as the power gets larger, they kind of flatten out near the origin. And they grow a little bit faster as you move away from the origin. The odd power functions all kind of have this S-curve shape. Right, so here's x cubed, x to the 5th, same sort of S-curve shape, but again, it's a little bit flatter near the origin. And as that power goes up, the flatness becomes more severe. Other ones we looked at, like the square root function. Type it as a 1/2 power square root function. The 4th root, same sort of patterns. 6th root, if you look at even roots, these are actually, if you kind of turn your head sideways and look at these, you'll realize that these are 1/2 of the sideways parabola, or like this is 1/2 of a sideways parabola. Here's the other half. And the pattern that you notice between the power functions, the same pattern shows up with the root functions. So like if I turn off this guy, I turn on the 1/4, and I switch this to a 4 down here. Right now, that's that same bowl shape as x to the 4. It's just like rotated 90 degrees to the right. So the root functions demonstrate the same sort of patterns there. And we can look at the odd roots. Same things going on. Here's the cube root. It is the same thing as the graph of x cubed, just reflected over the line y equals x. And the 5th root and the 7th root, and the same patterns that you observed in the integer power functions show up here. It's just that the graphs are rotated 90 degrees to the right, or if you like, reflected over the line y equals x. In this context, it means the same thing. So those guys, together with these guys, and the absolute value function, we'll call those parent functions. And what I mean by parent functions is they're going to have babies. We're going to make other functions out of them. So here's the first few reciprocal power functions, or power functions with a negative power, 1/x, 1/x cubed, 1/x to the 5. You'll notice they all have the same sort of symmetries, and they all have the same sort of basic shape. But again, the shapes are slightly different. Here, as the power gets larger, the graph of the function wants to sit down on the x-axis faster. That's really what's happening. And if we change the odd powers to even powers, the symmetry again goes from a sort of origin symmetry to a y-axis symmetry. And the same sort of shit happens, that as the power goes up, the curve wants to sit down a little bit faster, a little bit harder on that x-axis. So here's 1/x squared. Here's 1 over x to the 4 in blue. Here's 1 over x to the 6 in green. If you're not intimately familiar with the graphs of all these functions, I want you to make flashcards, or I want you to, get out your notebook and draw each of these graphs by hand with a table of values. That's how you get to know these things. Think of them as your friends, right? You're going to sit down and write a little bit about your friends in your journal. That's what you're going to do, because you need to get to know these. So your knowledge of these is what's going to allow you to do all the shit we need to do in section 2.6. We will use these as our basis for transformation. The graph of the absolute value function, we talked about that the other day. That's that piecewise V-shaped function. So that's the sort of preliminary stuff here. If you don't know these, please get to know them. Get to know them well. We're not asking a lot here because they have so much in common. So only a few sort of basic shapes. All right. There are 4 basic transformations that I'm going to mess with. I'm going to make you learn. But 2 of them have special cases that most people think of as separate. There's something called a horizontal scaling. That's where I stretch or squish together a graph horizontally. There's something called a horizontal shift. That is what it sounds like. That's where I take a graph and I drag it to the left or I drag it to the right. There's something called a vertical scaling. Which again is what it sounds like. That's where I kind of stretch a graph out or compress it down vertically. And then there's a vertical shift. You can make this shit complicated if you want to, but it really doesn't need to be. I use the word scaling here for a particular reason, because that's literally what we're doing. You scale something up, you scale it down. It means to multiply by a number. Right? So in fact, the higher order math name for numbers is a scalar. So a horizontal scaling. This is like, this is obtained from the graph of f of x by multiplying on the inside by a constant. And I'll tell you the exact rules, right? Like if c is bigger than 1, then you're stretching. If c is smaller than 1, you're shrinking, whatever it is. I'll tell you that in a minute. But if you multiply on the inside of a function by a number, that's going to scale the graph of the function horizontally. A horizontal shift is what you get if you add or subtract on the inside by a number. I'm going to write it like this for reasons you'll see soon. A vertical scaling comes from multiplying on the outside of your function by a number. And a vertical shift comes from adding a number on the outside. So if you see something that looks like this applied to one of your parent functions, then you should be able to figure out what the graph of those things are by taking the graph of your parent function and applying the appropriate transformation. All right, let's, I think the best way to kind of get comfy with these is really just to look at a few examples. And I'll justify them for you as we go. I'll hold here just for a second. Anybody? Second. Okay, here we go. Okay. Beginning with the graph f of x equals, start with one we all know, x squared. Transform to get the graph graphs y equals x squared plus 3. Y equals x minus 2 squared. Start here. Turns out shifts are a little easier than scalings to think about. And vertical shifts are a little bit easier to think about than horizontal shifts. I want to point out that in part A here, x squared plus 3, this is f of x plus 3, because f of x is x squared. My parent function here is x squared. In part B, what is x minus 2 squared? Can anybody tell me how to write that in this function notation?
You would put the f parentheses x minus 2 parentheses.
Very good. This is f of x minus 2. Okay. So do we see what kind of transformation we're talking about here? What is this? From that list on the previous page.
Horizontal shift.
Very good. Yeah, this is a horizontal shift. And this guy?
Vertical scaling.
It's a vertical something, but it's not a scaling.
Yeah.
Yeah, this one's a vertical shift. If I was multiplying x squared by like 3, if it was 3x squared, that would be a vertical scaling. All right, I'm going to begin with a little sketch of the parent function. This graph looks like, well, we all know it. But I'm going to label a few points. And the rule I'm going to have for you guys, and you do this on your test, you're going to have to label at least 3 points explicitly anytime I make you graph something. So here's 3 points labeled explicitly. And by explicitly, I mean like with the ordered pairs. All right. I want you to look at the formula here. Remember, the y values everywhere on this graph is equal to the square of the x values. That's what it means to say we're on the graph of x squared. Here, I'm looking at y equals x squared plus 3, or y equals f of x plus 3. So what we're really doing here in this guy is we're adding 3 to all the y values. That's how we're going to get the graph of this thing in part A from the graph of the parent function. So here's my solution for part A. I'm going to take the graph of the parent function there, and I'm going to add 3 to all the y values. So I have this point here, 0, 0. If I add 3 to that y value, that becomes 0, 3. I had the point -1, 1 on my original. So if I add 3 to all the y values, that means that point is going to become -1, 4. And I had 1, 1 on my original, on my parent. So if I add 3 to the y values there, that's going to become 1, 4. So here's your new graph. It's been shifted up by 3 units. Does everybody understand what I'm doing here and why it is moving up by 3 units?
Yes.
It's not too crazy, right? It kind of makes really good sense. Now, I'll warn you in advance, this one, not as easy to see. I'm not going to subtract 2 from all the y values. I'm going to give you a second to think about that while I refresh my coffee. I want you to try and think about what sort of shift we're going to see here and why. I'll be right back. Alrighty. So what direction am I going to transform or shift this graph in order to get the graph of this function?
2 to the right.
2 to the right. That's correct. Would you care to explain why?
Because we kind of see it up there where you do the horizontal shift, it's x minus c. So that would be, since it's x minus 2, that's +2.
That's good. Yeah, that's definitely why I chose to write it in that way. And that's how I remember it. That's how everybody remembers it. So that's great. One way to think about it is to ask kind of what it does to individual points. Like here we added 3 to all the y values. If I want to keep the y value of 1 at this point, let me focus on this point for now. If I want to keep that y value as 1, I have to ask what's going to happen to the x value when I apply this transformation. Well, to get y equal to 1 here, I need the inside of this to be either 1 or -1. To get the inside of this to be 1, x actually has to be 3. So kind of the thing that I encourage people to remember is that the horizontal transformations sort of do the opposite of what the algebra suggests they would do. We're not going to subtract 2 from all the x values. We're going to add 2 to all the x values. So in order to maintain the y value that we want, we have to add 2 to this x value. We have to add 2 to this x value. We have to add 2 to this x value. And the effect is going to be to drag the whole graph to the right by 2 units. So 0, 0, he's going to get dragged to the right over to 2, 0. 1, 1 is going to get dragged to the right to 3, 1. And -1, 1 is going to get dragged 1, 2 to the right to 1, 1. And here's your graph. So this was a shift up by 3 units. And this was a shift right by 2 units. The graph here is That's the one we want, y equals quantity x minus 2 squared. Okay, so stuff that happens on the inside of a function does horizontal things. And modifying the outside of a function does vertical things. If you add a number on the outside of that function, that's going to shift you up that many units. If you subtract a number from the outside of the function, that's going to shift you down that many units. It's very intuitive. The horizontal stuff, less intuitive. If you subtract a number on the inside of the function, that's going to drag you to the right by that many units. And if you add a number on the inside of the function, that's going to drag you to the left by that many units. Okay. So let's come back here. Yeah. Okay. I want you to come back to this spot in your notes. And I want you to annotate this with some details. So here, if you add C on the outside, the graph goes up C units. And if you subtract C on the outside, the graph goes down C units. And putting it that way, we're assuming C is positive, right? You add on the outside, graph goes up. Subtract on the outside, graph goes down. This one, same sort of thing. I can say if you subtract C on the inside, graph goes right C units. And if you add C on the inside, then the graph goes left C units. Those are the shifts. The scalings I want to talk about in a little bit more detail, because it doesn't just depend on the sign of C, that does matter, but it also depends on the size of C, whether it's bigger or smaller than 1. So the two that have like easy rules are the shifts. Okay. Let's look at some examples of scaling. We'll talk about reflecting in a little bit. Let's take a graph we know well. I don't want to use x squared again, though. So let's use x cubed. So use the graph of f of x equals x cubed to sketch f of x equals 1/2 x cubed. F of x equals let's do 2 all cubed. So here I've multiplied on the outside by 1/2. And here I shouldn't call these f of x. I'm sorry. Let me just call these y. I'm sorry, because we've already called this thing f of x. And the first one I've multiplied on the outside by 1/2. And the second one I've multiplied on the inside by 2. And those are both going to be scalings. The first one is going to be a vertical scaling. And the second one is going to be a horizontal scaling, right? Inside stuff, horizontal, outside stuff, vertical. This first guy, I could write him as 1/2 f of x. And this guy I could write as f of 2x. Right? So let's take the graph of our parent function. And again, I'm going to make sure I label plenty of points on this. Mark this as 8. This is 1. 2. 2. So 0 cubed is 0. 1 cubed. 1 cubed is 1, and 2 cubed is 8. That's why I'm choosing the kind of tall scale here and the wide scale here. -1 cubed is -1, and -2 cubed is -8. So the shape of this graph is the shape that we know. It's kind of this curve. The logic that we used for the vertical shift, we can apply to the vertical scaling also. Really what we're doing here is we're multiplying all the y values by 1/2. So for part A, what we're really doing is all the y values by 1/2. So this point over here is 2, 8. This point here is 1, 1. This over here is -1, -1. This over here is -2, -8. So if I multiply all the y values on that graph by 1/2, that's going to scrunch it down. And I'm going to label some points on the resulting graph so you can be 100% sure what everything is. If you take the point at the origin, 0, 0, and multiply that y value by 1/2, 0 times 1/2 is still 0. If you take 1, 1 and multiply that y value by 1/2, you get 1, 1/2. And if you take 2, 8 and you multiply that y value by 1/2, you're going to get 2, 4. And then symmetrically over here, everything, all the same stuff happens. So -1, comma, -1/2. And you'll have -2, comma, -4. Still the same shape, same overall shape, just shortened, squished down, kind of like one of those funhouse mirrors that makes you look fat. The graph has been squished down. And I can show you in Desmos on the same coordinate axes. You get a slightly better feel for the scale. Right. Compare the black, which is the parent function, to the blue. If you look at any particular x value, you'll see that the height on the black is twice as high as the height on the blue. So this is a vertical compression. It gets squished down or squishing. For the other guy, we're going to do something else. We're multiplying on the inside of the function by 2. And remember what I said, that kind of the horizontal transformations do almost the opposite of what the algebra suggests. So we might think, oh, okay, this means I'm going to multiply all the x values by 2. But that's not what we're going to do. We're actually going to divide all the x values by 2. So just like with the shift, things go in the opposite direction, you would think. Here, what we're going to do is and you can follow the same sort of logic that we used when we talked about the horizontal shift. If I want to take this point 1, 1 on the parent function, for example, I want to know where that point gets moved to by this transformation. Well, if I want to keep that y value as 1, what does x need to be in order to get the y value of 1 out? I need 2 times x to be equal to 1, which means x has to be 1/2. So really, multiplying on the inside here by 2 means we're dividing all the x values on the graph by 2. Try to give you a feel for what that looks like here. We'll look at it in Desmos just to again make sure we have a good scale. Try to draw this the same scale that I did up there. So I'm going to take all these x values on the graph of the parent function and divide them by 2. So 0, 0, if I divide 0 by 2, I still get 0. 1, 1, if I divide this x value here by 2, I get 1/2. So that's going to be 1/2, 1. There's that. 2, 8. If I divide that x value by 2, I get 1. So it's going to be 1, 8. Same thing happens to these guys. -1, -1. If I divide that x value by 2, I get -1/2, -1. And then -2, -8. If I divide this -2 by 2, I get -1, -8. All right, so here's the result. So this is a horizontal compression or squish. By a factor of 2. Interesting stuff, right? Questions about how we're getting either of the purple graphs here from the black graph?
So for when we have questions, is the question gonna ask specifically for the X values and the Y values, right?
So the types of exam questions I could put on here, I could give you a particular function and say, sketch the graph of the parent function, right? Tell me what the parent function is, sketch the graph, label 3 points on that graph, and then sketch the given function, the transformed one, label 3 points on that graph. I could also just give you some, some transformed function algebraically and ask you what transformations do you need to apply to get this graph from the parent graph. You will need to label points on the problems that actually ask you to graph things. And you may also be told to describe transformations. Am I answering your question? Is that what you were asking?
Well, yeah, but what I was asking was if, like, for example, the questions are gonna say like you need to divide the X values or you need to divide the Y values specifically, or we like do both, or just
you will have to be able to tell what to do, right? So the question won't tell you to do that. The question will just give you the function and you'll have to remember what to do.
Oh, okay. Thank you.
Cool. All right. So that's each of those separately. There's a couple other things I want to talk about from this section. One of those things is symmetry and reflections. So with the vertical and horizontal scalings, right, where you're multiplying on the inside or outside by a number, if that number isn't positive, the graph is going to flip over either vertically or horizontally. It'll flip either over the X or the Y axis. And functions that are invariant under those sort of reflections have special names. So I want to show you what those special names are after showing you the reflections, and then we're going to look at kind of putting it all together, doing 3 or 4 transformations all at once. But first, let's come back and make another little note here. So for this guy, I'll say if C is bigger than 1, then this will be a horizontal shrunk, compression, squish, whatever word you like. And if 0 is less than C is less than 1, C is positive, but smaller than 1, then this will be a horizontal stretch. There's going to be a little bit more to say about these regarding reflections, but this is the basic stuff. All right, and this guy I'm going to take down here, where I've got a little bit of room. This one is more reasonable. If C is bigger than 1, then this will be a vertical stretch. And if 0 is less than C is less than 1, if the C number is positive but smaller than 1, this will be a vertical shrink or compression or squish. All right, these are the basic rules. Now, like I said, there's kind of one way these things can get more complicated, one case that's not discussed here so far. Here, if C is bigger than 1, if C is between 0 and 1, what if C is negative? It's not being described here. And similarly, if C is bigger than 1, if 0 is less than C is less than 1, well, what if C is negative? Both of those involve the flipping operation. Let me hold here just for a second. Make sure you guys have time to get this in your notes. Okay. Let's sketch y equals negative absolute value of x from a table of values. Might seem like a change of pace, but I promise you it's going to connect to what we're doing. Focus. All right. So I'm just going to make your regular old XY table. If you plug in -3 for x here, what do you get out for y?
3.
So the absolute value of -3 is +3, but this is negative absolute value of -3.
-3.
Benefit.
Yeah, this is going to be -3. And same sort of, if I plug in -2 here, the absolute value will make it positive, and then the negative will make it negative again. If I plug in -1 here, the absolute value makes it positive, and the negative makes it negative again. If I plug in 0, I get the absolute value of 0, which is 0, and -0 is still 0. What if I plug in +1?
-1.
The same.
Good, yeah, -1 and same pattern, right? Just like that. Hugo who said that? You got the same pattern. Okay, so I've got my table of values. Let's draw the graph. When x is -3, y is -3. When x is -2, y is -2. When x is -1, y is -1. When x is 0, y is 0. When x is 1, y is -1. When x is 2, y is 2. And when x is 3, y is -3. So the graph here is like this. Modulo my bad art. What's the relationship between this graph and the graph of the regular absolute value function?
It's flipped over the x-axis.
Yeah, it's been flipped over vertically. It's been flipped over the x-axis. So the graph has been flipped vertically. And by that we mean over the x-axis. So if you multiply on the outside by -1, that flips your graph over vertically because it negates all the y values on the graph. You can combine this with the regular vertical scaling rules. So I'd say, multiply by -3 on the outside of your function. That's going to do two things. It's going to stretch your graph by a factor of 3 and flip it over the x-axis, flip it over vertically. All right. So there's an extra rule here. New rule for vertical scalings. If you multiply on the outside by a negative, the graph flips vertically. Or over the x-axis. And now that's the full set of rules for vertical scalings. Right? You've got the stretch and squish rule. And then also if there's a negative outside, that's going to flip you over vertically. There's a similar thing for horizontal scalings. If you scale horizontally by a negative, that will flip you over the y-axis or flip you over horizontally. And I'd like to look at an example of that. So let's do that. What's a good example function to do this with? Most of our functions. Oh yeah, I got it. Okay. We're going to sketch by making a table of values. We're going to sketch the graph y equals the square root of negative x by making a table of values. And then we'll compare it to the graph of regular old square root x. I know a lot of people see this and kind of alarm bells go off in their head right away because they're like, you can't have a negative under a square root. And it's true, we don't like taking square roots of negative things. But if x is itself negative, then negative x will be positive. So I think we're about to get a little, hey, Nova Kitty. Yeah, go ahead and bring him in. This is one of the animals running around the house. Everybody say hello to Nova Cat. He's grooving, just doing his thing. If x is itself negative, then negative x is positive. So the negative under here, it's going to change the domain, but it doesn't mean like there's some deep existential problem. Well, let's make a table. Actually, let me do a -4. Pick some values here that'll give us nice outputs. -4, -1, 0, 1, 4. Picking perfect squares because we're going to try to take the square root. So if I plug -4 into this function, what do I get out for y?
2.
2, right? -4 is +4. The square root of +4 is +2. If I plug -1 in here, I get -1 inside the square root, which is +1. The square root of 1 is 1. Is it okay to plug 0 in here? What happens if I plug in 0?
You just get 0.
Yeah, -0 is 0, and the square root of 0 is defined. It's 0. It's all right. And because 0 times 0 is 0, we can say that the square root of 0 is 0. What happens if I plug in +1?
You would just get I.
Yeah, technically we would get I and 2i here, but they're not real numbers. We get non-real complex numbers for our output, and we don't like that. We're not going to mess around with graphing complex valued functions. You need 4-dimensional graphs to do those. You want to learn that shit, come see me in complex analysis. I'd be happy to show you. But for us in regular calculus and definitely in pre-calculus, we're not messing around with complex outputs from functions. All right. So I don't have anything in on the right-hand side, but I do have some stuff on the left-hand side. Got 0, 0. This is 1. This is 2. We've got -4, comma, +2. -1, comma, +1. So here's my graph. And if you compare this to the graph of the regular square root function, what do you notice?
It's flipped.
Good. Flipped how?
It's flipped horizontally.
Yeah, it's been reflected or flipped horizontally about the y-axis. So that's alluding to our final rule for transformations, which is if you multiply on the inside by a negative, then you'll reflect the graph horizontally. Okay, and now we have everything that you need to know about transforming graphs of functions. You know how to flip vertically, flip horizontally, stretch vertically, squish horizontally, squish vertically, slide left, slide right, slide up, slide down. You can do it all. One last thing. Most of the time, when you're solving problems like this, you're going to have more than one transformation going on. You're going to have a vertical shift and a horizontal scaling and a vertical reflection, all of that shit put together into one thing. You got to do it in this order. You got to do it in this order. That's why I put these in the order I did. Horizontal scalings first, and that includes horizontal reflections, right? Reflections are scalings. They're just scalings by a factor of -1. So horizontal scalings always come first, including reflections. Then horizontal shifts. Then vertical scalings, including reflections. Then vertical shifts. The order matters. These don't commute. All right. So one more time, the order here matters. There are some cases where you can get away with doing things out of order, but in general, the order does matter. And if you're getting one of these wrong, you should ask yourself, am I doing this in the correct order? Or if you're having trouble seeing why the correct answer is what it is, because let's be real, it's WebAssign. It's not going to tell you your graph is wrong. It's just going to say that you picked the wrong graph from theirs. Ask yourself, am I doing this in the correct order? So horizontal scalings, including reflections. We can add these here. If C is less than 0, then there's a horizontal flip. And here, if C is less than 0, there's a vertical flip. And then really what we can do is we can modify these to say the absolute value of C and absolute value of C, absolute value of C, absolute value of C. All right, so if the size of C is bigger than 1, say for a horizontal scaling, then you're going to be doing a shrink. And if it happens to be negative, you're going to be doing a shrink and a flip. Let's look at some examples. How's about, yeah, I like this, okay. So if I want to sketch the graph of 1 minus the square root of x using transformations, then I need to first figure out what my parent function is. Then I need to figure out what my transformations are. Then I apply those transformations one at a time to the graph of the parent function until I'm satisfied that I'm looking at the graph of this function. First, what's my parent function?
Square root x.
Good. Okay. What are my transformations? Anyone want to guess?
The negative and the 1.
Yeah. So here's my advice. Let's rewrite this to make it look like the definitions of the transformations we have. So y equals 1 minus the square root of x. That's really the same thing as saying negative square root of x plus 1, right? Is everybody comfy with that? Like 1 minus 3 is the same as negative 3 plus 1. 1 minus root x is the same as negative root x plus 1. So what transformations do I see here? Well, this is going to do something, and this is going to do something. Is this negative multiplying on the inside or outside of my parent function?
Outside.
Good. So what is this negative going to do?
Flip it vertically.
Good. In particular, I would say this is a vertical scaling. And it's, like you said, it's just a flip. It's not stretching or squishing anything. It's just the flip. Is this happening on the inside or outside of my parent function?
Outside.
Outside.
Yeah, excellent. So this is going to be a vertical shift. And in this case, we're going up 1 unit. All right, so we're adding 1. Which should I do first?
The flip.
The flip first, right? So our order is horizontal scalings, horizontal shifts, vertical scalings, then vertical shifts. So first I do the flip, then I do the shift up 1. Beginning with the graph of square root x. Remember, we got to label some points. So here's 0, 0. Here's 1, 1. And over here is 4, 2. Beginning with the graph of the parent function. We then scale vertically. So we're going to flip it over. And as we do this, we're going to track what happens to those points. 0, 0 is going to stay 0, 0. 1, 1 is going to be flipped to 1, comma, negative 1. And 4, comma, 2 is going to be flipped to 4, comma, negative 2. So this is just the flip. First one's the graph of the parent function. This next one is the graph of that first transformation that we applied. And now we're ready to graph the final thing by bumping all these points up 1. So I'll save space here. That's what I was doing for my big graph. Big graph's going to be the final one. 0, comma, 0 is going to get bumped up 1 to 0, comma, 1. 1, comma, negative 1 is going to get bumped up to 1, comma, 0. And 4, comma, negative 2 is going to get bumped up 1 to 4, comma, negative 1. Okay, so here's my picture. Doesn't have to be perfect. My pictures aren't perfect. I don't expect your pictures to be perfect. That's one of the reasons we label points. So 0, 0. Here's 1, 0. And here's 4, negative 1. And this is the graph we wanted. Y equals negative square root of x plus 1, which is we're asked to graph. All right. So you do the transformations, you do them in order, draw the graph, track a few points along the way, and you'll be good. Questions on this guy? Okay, let me try one more on you. And then we will finish this section here by talking about symmetries. How am I doing on time? How'd you guys-
Professor, it's 2:50.
Ah, shit, we're right at time. Thank you, thank you. All right, so we didn't actually finish 2.7, or sorry, what is this, 2.6 transformations? Yeah, we haven't quite finished this yet. We still need to talk about symmetries, and then we'll need to talk about combining functions. So the remainder of this section and the section on combining functions will have to wait until Monday. That's okay. Like I said, we may end up pushing that test a little bit, but for right now, you can count on having exam 1. What date did we say? This page back up here. You can count on having exam 1 on the 8th, which is next Thursday, right? And remember the homework.
Right? We get Monday off.
That's correct. Yeah. Monday we have off. I'm sorry. Monday is off because the 4th of July is Sunday. So homework 1 is due on the 5th. That's next Monday. Homework 2 is due on the 7th. That's next Wednesday. We'll finish the transformations of graphs and combining functions material on Tuesday of next week because Monday we don't get to meet. And then exam 1 is currently scheduled for next Thursday. I may change this, may not change it. But for now, put this in your phone, put this in your schedules, plan for the exam to be on that date because I suspect we will be ready for it by then. Remember, graph the functions in the homework by hand unless the problem explicitly tells you to use a calculator. You need that practice. I promise you, you need that practice. Do that, you'll get good. Any questions for me before we depart?
I had a question from the homework.
Sure.
It was from the first homework.
I see. I've got 246. Maybe my clock is slow. Yeah, what did you want to see from homework 1 there, Oscar?
Give me 1 second. I'm trying to find it. Yeah, 59.62.
Said 59.
Yes.
Okay. 7, 59. Okay. So I say the function f is graph below. It's a polynomial of degree 4. Use the graph to answer the following. Find f of a from the graph. Let me see the graph. Find the height above. Okay. So this is, they're kind of asking in the abstract here. If you wanted like f of 7 or f of pi or f of 12, you would look for the y value or the height above the of the graph above the x-axis at x equals a. So then if you want to know what f of 2 is, you come to the graph here, you go over to x equals 1, x equals 2, and you come up here and you find this height. So here, whoop, can I not? I gotta move this thing. This would just be a. And then your graph might be a little bit different than mine, but whatever the height is here. So if this is 3, right, 1, 2, 3, then each tick mark is 1, 4, 5, 6, 7. And I'll let you complete this last guy here.
That was my question. So I thought it would be. I think we got the same graph. Let me check. Yeah, I put on the last line f of 3 minus f of 1 equals 2, and it says f of 1 is correct, 2 is correct, but 3 is wrong.
So you may have different numbers than I do here. Mine is asking for the net change
Oh, I see.
x equals 1 and x equals 2. So make sure you're reading that carefully. It would be f of whatever the larger of these two numbers is minus f of whatever the smaller of these two numbers is. So for the numbers I've been given here, this would be f of 2 minus f of 1. F of 2 for me is 7 here. F of 1 for me, what was that? It's 1, right? So for me, this would be f of 2 minus f of 1, which is 7 minus 1 would be 6. So I'd say read this very carefully, make sure that you're using the correct values that they gave you. And then remember that you want f of 2 minus f of 1. So you need to be subtracting the y values here. Does that make sense?
I have so I have the same graph, but I have the net change between x equals 1 and x equals 6.
Okay.
So,
F of
so
6 is 3, right?
yeah.
And f of 1 is 1.
Yeah.
So that would be, did I read that right? 1, 2, 3. Yeah. So f of 6 minus f of 1 for you would be 3 minus 1, which is 2. Yeah.
Oh, I see. Okay, I put f of 3. I was doing the y value.
Yeah. Okay. Yep. So pay attention to the little bits that they fill in for you. It's kind of subtle here, but this isn't. They want f of blank. So we're inserting the x value here, and then for this box, they want the difference in y values.
Okay, I see.
All righty. All right.
Could we? You have time to look at another one?
don't see any harm in that. Yeah, I mean, after this, I'm just going to an office hour. What would you like to look at?
62.
Okay. So it says function value f of a is a local max value of f if f of a is the blank value on some open interval containing a. So what are we looking for here?
Largest.
Mhm.
And then it says I got all of them right except for the first fill in where it says one local maximum is blank and occurs at x equals, mine says x equals 2. I think yours says the same.
Okay. So what did you enter in the blank here?
2,7 in parentheses.
So be careful. This is that language thing we were talking about last time. If I ask you what is the local max, that's the y value. And if I ask you where is the local max, that's the x value.
Okay, so it only wants the y value?
Right. So remember what is the max? That's the output there. I want to know, like, this is the largest value that comes out of the function. So they're asking specifically for the y value.
Okay, yeah, that was my only question on that one. Thank you. Okay, thank you. Appreciate it.
Alrighty then, guys, we are about 3 minutes over time, so I'm going to go ahead and end the meeting. If you do want to talk more about anything, talk homework problems, whatever, just come to the office hour. Office hour starts in 7 minutes. Otherwise, hope you guys have a lovely weekend. Enjoy your holiday. Please be safe. Do not drink and drive. I will see you on Tuesday. Goddamn mouse.